Okay, so in this video I'd like to continue the discussion on maximum and minimum points and how they can be used in applications. For this particular problem we have a box that's going to be made with an open top, and to form this box we're going to take this square. We've got this square sheet of cardboard and we're going to cut corners out of that cardboard, and if we were to cut these corners away, then we can fold along these dotted lines, and as we fold them up, we should be able to create this box that we see over here on the right-hand side. Now the question is going to be, what's the best size of the cutout supposed to be? How large is X going to be? How much should we cut out from each corner to hold the most amount of stuff, the largest volume in this box on the right-hand side? So if you think of it, if X was larger, if we had a larger X value, we'd cut out more of that corner. And if we were to fold the box along these lines here, it would have a smaller base. The base would be a little bit smaller, but the height would be a little bit taller because each of these sides, when folded up, would reach a little bit higher. And that's going to affect our volume. It's not going to be the same as this original sketch. And so with X being a variable, with X changing, what position or what value of X is going to give us the maximum volume for this box? And so we've got to remind ourselves here that length, width, and height are the three measurements necessary to find the volume of a box, and volume is equal to simply the product of length times width times height. So if we're starting with this net, we call it, this flat shape that's going to get folded up into the box, the width of the box might be represented by these sides here. This is the width. And since the cardboard was a square and it's 30 inches wide and 30 inches long, then the width of the box itself is going to be 30 minus 2x, because this length of this blue line is 30 inches minus this x and minus this x in length. Similarly, the length of the box, if we consider that along this edge here, that's also going to be 30 minus 2x. And then finally the height of the box. Now remember that this side, these are all going to be folded up towards the top here where the arrows are pointing. So the height of the box is simply x. After we cut these corners out, here's our height of the box, and they're going to fold together and form the side edge, or the fold towards the top of the box. And so with that in mind, we could say something like this: the volume of the box based on the x dimension that we settle on is simply length times width times height. And I'm going to write it this way. Our height was x, our length was 30 minus 2x, and our width was 30 minus 2x. And while the answer could be left in factored form, like it is here, I think with a little bit of effort we could combine by foiling and distributing to a polynomial that looks like this. And I prefer this answer in this case here. With this equation, we can now graph like we've done in the past to find the x that maximizes the volume. So go ahead and pause the video now and open up a graphing calculator, either your TI Nspire program or, say, Desmos in this case for practice, and find the value of x that does maximize the volume. Resume playback in a moment to check your work. So off screen I ran my TI Nspire and I did graph the function 4x cubed minus 120x squared plus 900x. I found that a window of -4 to 20 on the x-axis and -300 to 3000 on the y-axis was appropriate. That displayed this curve, and this point right here was found to be a local maximum. So that point occurred at the coordinate 5, 2000. with 5 being our x value, the size of the corner cut, 2,000 being f of x, or in this case, v of x, volume based on x. So it's safe to say that an x value, which was again representing our corner cut of 5, if we cut 5 units out of each corner, will maximize the volume, because the volume at that point would be 2,000 cubic inches. If we'd only cut 4 inches, well, if we follow 4 up from the x-axis, that's going to create a box that's pretty large, but it's not quite at the maximum. If we cut a corner out of 6 inches, well, similarly, we're going to see a problem there. If we had a box cut with 0 inches cut away, well, we can't actually fold the box up at all, so we'll have a volume of 0. And if we were to cut 15 inches, this spot represents 15. If we were to cut 15 inches in from the edge of the box, well, we'd have a problem there too, with the box only being the cardboard only being 30 inches wide. If we try coming in 15 inches from the edge, well, then we would have no box at all, because that would be too far. This portion of the graph over here on the right-hand side is not very useful for our real-world consideration, because we can't cut 16, 17, 18, or so on inches in from the edge. So we'll kind of ignore that portion of the domain. Now, to answer part C, we could do much the same technique as we've done in the past and create a horizontal line at our target of 1,500 inches. So go ahead and pause the video again and try to find this solution. Pause the video and come back to check your work in just a moment. And so, as I illustrated in the last video, we can create a second equation. In this case, f of x equals 1,500. That's our target. We were trying to find a box that holds exactly 1,500 cubic inches. Maybe this is necessary for a product that's being sold. And we can do so by cutting a corner out of the original sheet that's 2.3 inches in length, or we could do the same with a cut that's 8 inches in length. So essentially, we can create a shallow box by cutting this corner. We can create a taller, narrower box by cutting this much out of each corner. And so an x value corner cut of 2.34 when rounded and 8.26 both would produce a box that holds a volume of 1,500 inches. Now, for the next questions, I'd like for you to read through the problems and see if you can match this story, quote story, A, B, C, and D with options 1, 2, 3, and 4 below. Which graph would match the scenario A, B, C, and D? Pause the video and resume playback in a moment to check your work. And I think these solutions would be fair. Story C, a car is driving on the interstate and its distance from a city decreases at a constant rate. So if the y-axis represents our distance and the x-axis represents time, as time increases, our distance from a city decreases, and it's doing so at a constant rate. It's a constant decrease in distance. Constant rate meaning straight line. For part B, a country's population that increases more rapidly over time. A population over time might increase slowly at first, but as more and more people move to this location, this country, the population may increase more rapidly. And we'll notice how it gets a little bit more steeper from left to right. Story D, a ball is dropped from the roof of a building and its height above the ground decreases over time at a faster and faster rate. So as you first let go of an object, it starts to fall, but it's falling fairly slowly at first. It's not very steep, and as it picks up momentum towards terminal velocity, its speed will increase in this downward direction. So again, we're creating a steeper line, this time a steeper line in a negative direction, negative slope. And so that leaves option A, or story A, with this temperature of a cold drink that warms up over time. So we might have temperature over time. This cold drink will warm up fast at first, but as it gets closer to room temperature, while it still increases to temperature, it increases at a little bit of a slower rate. And we have this horizontal asymptote at which the temperature would approach. Now, to add to our calculus preview, being in this college algebra course, we're going to introduce this concept of concavity, this notion of a graph being concave up or concave down. Now, we've already talked about increasing versus decreasing. When a function is increasing from left to right, it's going up from left to right, and when it's decreasing, it's going down from left to right. This notion of concavity talks about the curve of a graph and whether it's curving up or curving down. And so what I like to tell students is that if they think of a smiley face, if you've got a smiley face that's drawn, a smiley face is concave up. If you focus on the mouth of that smiley face, you can see that the ends of that curve are sort of angling upward. If we were to look at a frowny face, that's what I would say is concave down, and a person who's down has a frown. So this is concave down because the ends of that graph are pointing down. Now, not all graphs look quite like a smiley face or a frowny face, and instead they've got portions of each within the graph. And if you take a look at this example here, and I'll pick some colors to make this stand out, this portion of the graph, this little section from here to about here, that curve is kind of a frowny face. That's curving down. So I would say that the concavity there is down. From this point, we switch concavity and we start curving up again. And while we don't curve up like a true smiley face, hopefully you can see that this section of the graph is starting to curve upward again. It's bending back towards up on either end. And so we would say that section of the graph is concave up. And then here again, the graph starts to turn downward or bend downward, and it's concave down across this section of the graph. So again, similar to increasing versus decreasing, we have portions of each within this graph. But if we were to answer the question, the interval on which the graph is concave down, I would say that on the interval from 0 to 2 and from 4 to 7, we have a graph that's concave down. Although this is kind of hard to see with my scale here. Let me try to make that a little bit more clear. I realize my grid lines are conflicting with the grid lines of my paper. So let's try to make this a little bit more clear. We've got an x value of 4 where the concavity changes, and an x value of 2 where the concavity changes. And so that's why I like this interval for concavity. The concavity behaves a little bit differently than increasing versus decreasing, and we can say that at 0 the graph is concave down. So we're going to include 0 with the square bracket, and same thing with 7 at the end here. We're going to use a square bracket there. So if you can ignore this notion of concavity for just a second, go ahead and try to answer part A and part B regarding maxima, minima, and functions that are increasing and decreasing. Pause the video now and resume playback in a moment to check your work. Okay, well hopefully you noticed that this is kind of an interesting graph in that it only increases from an x value of 0 to 1. In this short section of the graph it's increasing, but then everywhere else from an x value of 1 and on, the function is decreasing the rest of the way. And that's what we're saying here with our summary in this question. Part B only asked if there was a local minima, so we would say that there is no minima here because there's no point at which we switch from a decreasing graph back to an increasing graph. We have to switch from decreasing to increasing to locate a minima, so that didn't happen. But there was a maximum point, and that did occur approximately at 1, 6.5. So we switched from increasing to decreasing at an x value of 1, And as we switched from increasing and transition to decreasing, that location would be considered a local maximum. Oops, and I just didn't read ahead far enough. There was a maximum. Let's go ahead and copy and paste that down below. Now to answer the last couple questions, where is the function's absolute minimum and absolute maximum? Remember, another name for absolute minimum is called global minimum or global maximum. Those two mean the same thing. And this is the absolute, the highest and the lowest point possible within this function. So even though we don't have a local minimum in this particular graph, we do have a global minimum. Because if I were to erase this, we see that the graph sort of terminates at the end here. The graph terminates at the very end. So within this window, there is an absolute lowest point, and that absolute lowest point is down here. And so we could say that while there was no local minimum, there was no spot where the increasing versus decreasing changed properly, we could say that there is an absolute minimum at 7, 0. There's an absolute minimum at 7, 0. That's the lowest point within the window of this graph. As far as the maximum goes, well, that occurred at the same spot where our local maximum occurred. The highest point within the entire window, in this case, occurred where the highest point, where we changed from an increasing to a decreasing graph, where the behavior changed, and that was here at the coordinate 1, 6.5. And we already answered part F partially when we mentioned it up here. So this expression represents where the function is concave down. So I'll just copy this and report it at the bottom here. So we're concave down on this interval, and we would be concave up anywhere that the graph was curving upward. And that curve upward existed between these two x values, 2 and 4. At that inflection point, we don't have concavity. The concavity is technically 0 at the point of transition, so we're not going to include 2 and 4 in that domain of numbers, but anything in between 2 and 4 would be technically considered a concave up portion of the graph. Well, again, I hope this video helps, and I know it was a little bit more lengthy than the others, but there's lots of good stuff in here, especially when we're discussing vocabulary for this portion of the class. If you have further questions, please let me know. Thanks for watching.